Hey everybody, we are live. What questions are there? Who is here? 201, I see Dan's here. 320, 474. Who is here? Who is live? Put up some UT Marvel right there. Who is here? Who is live? Who is ready to ask questions? What do you have? Hey, what's up, Gigi? What questions do people have? Sorry, I got started 2 minutes late. 2 minutes late. I was running to my online office. Let's see what people have. Hey, Campbell, what's happening? Could you do homework 16 stock market question? You bet. And then we got question 1. So we got them in order right here. So we'll do homework 16 stock market question. And then we'll do 320. I can't even think. 320. I need some. I don't have water over here. No. I was eating some lunch. I didn't bring water. Let's take a look. I have questions about 201. You bet, Gigi. Let's do it. Hey, Meryl, how you doing? Doing well. We're pulling up the 201 as we speak. Getting 201 up. Stock market question. What's the stock market question? Is it on the quiz or is it on the homework? Is the stock market question on the quiz or the homework? So gold, I went from bronze to gold. Exactly. We even got a new status today. We made a new status this morning. We're always doing craziness right here. We're always going crazy. So we got it. It's on the homework, you bet. Let's take a look. Chapter 16, homework. Replace question. Okay. Let's see. Okay, let's go to the main screen. And let's do this. I'm good. Could we go over the homework commuter question? Yeah, we're going to do this. Then we're going to do 320. Then we'll do that one. You got it, Meryl. Good series of events right here. Let's go over to the main screen. Okay, we got the slot machine, company being sued, random poll. I think we did that one yesterday. Wait, is it on this one? I don't see the stock market question on this one. It's on the homework, Julia said. For me, it's question number 1 on the homework. Was I missing it? Maybe I skipped it. So is it this one right here? Homework chapter 16. Yeah, chapter 16 is a lot of terminology. This is it right here? This is it right here? Okay. So let's talk about this one. Okay, so what does the null always have? The null always has the equal sign. So whenever we write the null hypothesis, we can just put the equal sign instantaneously on it. So the null has the equal sign. Now we're asking, we want to see if a slot machine really wins 7% of the time. So is wins a categorical or quantitative question? Is whether or not the slot machine wins a categorical or quantitative question? Is winning a categorical question or quantitative question? Is winning categorical or quantitative? Whether or not it wins. It's categorical. So that means the answer must be what? And we don't use sample statistics here. We use population parameters. We use population parameters here. So what will be the answer? We don't use sample statistics for the null and alternative. We always use population parameters. So some of these are sample statistics. This is the sample mean. This is the sample proportion. This is the true proportion. And this is the true mean. So we will use P right here because P is the true proportion. So the true proportion is P and the sample proportion is P hat. Let's do a quick review. We'll show right here. We'll just make a quick table. And let's go here and do this. And let's go here to sample. My amazing handwriting. Population. Oh my gosh, I can do better than that. One of these days I'll learn how to write. There. Oh, that looks 50 times better. Sample, population, and then let's go here, and let's go here. And such a small box to write in. So we have here the mean. And the mean for the sample is y bar, and the population is mu, and the standard deviation is s or sigma, and proportion is going to be p hat or p. We can say the difference right here too, the difference between two means, diff and means. So the difference between two means is going to be y bar 1 minus y bar 2 over or mu1 minus mu2. Now, why is this so important? Why is this so important right here? These ones right here are what we use for the null, or the alternative also. Mu1 minus mu2 is the difference between means. P is when we test a proportion for the true proportion, and mu is the true mean. So all of these right here are used when we do tests on the mean. We'll be talking about testing the true mean, testing the true proportion, and you can see here the samples next to them. So kind of a really quick kind of cheat sheet right there. Make sure to write down. I write down so horribly, so you have to copy it, and you have to put in good handwriting. So let's go ahead and take a look right here. The true proportion is the proportion right there. And we're trying to see if it really is 7% wins. So we'll do the does not equals, and we got it. We're trying to see how much was spent on average on customers last year on a website. Nice job right there, Meryl. Excellent work. And we want to see if people are spending, let's see, has it increased? Now, what do you notice about this value right here? This value is quantitative or categorical? Is this value quantitative or categorical? So this is the big thing we have to recognize whenever we look at one of these questions. Is this quantitative or categorical? So that'll answer 3 of the spots. It's quantitative. So instantaneously, we know we're going with mu because we're not going to use the sample mean. We're going to use the true mean. And x bar and y bar are the same thing. You can call it x bar or y bar. You'll notice just different notation. It just means mean of variable x, mean of variable y. So you can call it your x variable, your y variable. I like to call it my y variable. So that's why it's just x bar in their notation. It's just mean of the variable they're talking about. And so the null has the equal sign, easy enough there. And we're looking at the mean, so it's quantitative, mu for mean and p for proportion. And then we're trying to see if it's increased. So we're just going to go there and do greater than. For the last one right here, we're going to do the amazing thing. It'll be the greater than because of the increased. Has it increased this year? So that'll be the greater than. So that's what they're looking for evidence of. Does that make sense, Meryl? Really good questions right here. And this is great practice. I really like this question a lot, because we know the null has the equal sign. Boom. A pharmaceutical company wonders if a cure rate is greater than 30%, and then we're asking what percent of people get cured. So is this P or mu? Is this P or mu? Because we're asking what percent of people get cured. And you think you either get cured or you don't get cured. Oh, no worries. This is good practice. It's really good practice. We're asking what percent of people get cured, and this is, yep, it's P. We're going to go with P right here. So all of these will be P. Whatever you answer for one is answered for the others. And it's proportion. And there we go. A bank wants to know if the percentage of customers using their website has changed. So if we're asking, has it changed, what will we put for the alternative? So remember, the null always has the equal sign. So we're always there. And we're going to go with P because we're asking, are they using our website? And P is proportion. And we're going to ask, not equal to. Yes. Who feels like this question's a lot easier now? Did this question get way easier right here as we show the steps, hopefully, to identifying, is it a quantitative number, so we're dealing with means, or is it categorical and we're dealing with proportions? So anytime you look at this, you should ask instantaneously, is it quantitative, is it categorical? And then you should ask, what's the direction of the sign of the alternative? Once you identify quantitative or categorical, the only other thing, you really only have 2 questions. You have, is it quantitative or categorical? And then what's the sign of the alternative? If you answer those 2, then everything else is, like this is the answer to one of them, and then all has equal. Great job, Julia. I'm really glad right there. I think we're going to hop right to 320. I'm going to try to do the questions in order. I see another 321. Ting Yang, good to see you here, Ting Yang. Didn't see that in the thing right there. We have 320 question 1. Which part of question 1? Is it with the weather part of it? Are you wondering about the weather part? I think that was Campbell. Did Campbell ask that? Are you wondering about the weather with the rain? I can actually do that one off the top of my head. I've done a few times. Is it the weather rain one? Let's take a look. I'm going to download the assignment. Are you talking about the logistic one? What's this? When dealing with proportions, are they more likely to be not equal to? It just depends on the wording of the question. So Campbell's saying, it's assignment number 9, right? Because that's the one due tonight, I think. Always look at the wording of the question. Let me speak to that briefly. Always look to the wording of the question to see if it's not equal to, greater than, or less than. Thank you so much, Ting Yang. You're totally right there. Yeah, well, we got those. Let's do a little 320 right here. We didn't do as much 320 yesterday, so we're going to do a little 320 right here. Then we're going to hop back to 201, and then we're going to do Gigi's question, and we got a lot more. So we're going to do a little 320 right here. And to answer Dan's questions very specifically, you always look to the wording of the question. This asks, has it changed? So you notice, has it changed is going to be the does not equal to. If they're asking, is it greater than, then you use the greater than sign. You always let the wording of the question tell you which way it's going. So this one wants to see if the spending at the website has increased, so we pick that. And this asks, is it equal to 7 out of 100? So the alternative would be it's not equal to. So if it gives no preference, you usually choose not equal to, but try to see if the question has a wording preference. And if it has a wording preference, that's the way we go. Let's look at some 320 right here. With 320, the first question is looking into whether or not it rains. And we're just going to look at the impact of rain. Is it EX4 bike? I think we're using EX5 bike. So we're going to look at the impact of rain. Yep. We're going to look at the impact on rain on demand. So we can use the associate function right here. Demand tilde. Why is my code going crazy? Weather, comma, data equals EX5. Change equals not equal to greater than. Exactly. Great job right there, Dan. You're 100% right. If it says has it changed, that would be not equal to. It could ask, is it the same? There's a lot of way to do the not equals to one, because it could ask, like, has it changed? Is it not the same? Is this still reliable? Is this still what we would expect? So when you see kind of no preference, that's when we look at, the change in it. So with this right here, we've got the associate function right here with demand, weather, and all this good stuff. And I think that's what it wanted us to do. What is the overall difference between rainy days and not rainy days? So what is the overall difference between rainy days and not rainy days? Can anyone tell me in the chat what we would do mathematically here to find out the overall difference between rainy days and not rainy days? What would we do mathematically right here? What could we look at in this output to look at the difference between the not rainy days and the rainy days? Exactly, Ting Yang, you got it. That's exactly it. We're just going to subtract the 2 right there. And they're not technically the coefficient, because this is the mean. You know what's interesting? If you went right here, it's so crazy. We're actually doing the chapter we just did for 201 just moments ago. We covered this chapter yesterday. And what you have right here is this is the sample mean for no rain, and this is the sample mean for rain. And what do you notice about this difference? This difference right here is what? So the sample mean for no rain minus the sample mean for rain, you can get the difference between the two, which is like 900 something, I believe. Is it 907? It's 907. And it's very significant. So there's a very statistically significant difference between the demand for bikes on days where it rains versus days where it does not rain. And you can see right here that this difference would be positive. So if we were to look at this in 201 output, you would have up here the difference, and the difference would be 907. So the difference right here in the 201 output would be that right there. Does that hopefully 201 sees it and it's like, oh. And then you actually have a discrepancy, which is a little bit different. It's a test statistic still, but not the t-score we're seeing for 201. It's actually done via simulation. It's actually an F right there, an F ratio. So this difference right here of 907 between these two numbers obtained by subtracting them is the difference of what we would expect between days where it rains and days where it does not rain. So that's good stuff right there. What other questions were there? I see, let me make sure I got them all and kind of do them in order. D2, we have D2, and we're going to go back and do some 201 here in a moment. I tell you, Office Hours Fly, we're already a quarter done with it. It's like, what happened? Great job right there, Campbell. Excellent work. Let's go to D2. What does D2 say? Fit the regression model predicting demand from these ones right here. Demand from effective temperature and day. Include a plot of the implicit lines when we predict demand effective day. Use the visual model after accounting for the effective temperature. Which day looks to have the highest? Is this the one right here, Ting Yang, you wanted? I know. I am just like, man, I tell you, I don't think I've ever been through a faster semester. I seriously looked and I was like, we have so many openings I haven't used in a while. Maybe I'll use my UT Marvel opening. I need to put them all on here as like their independent things. That way I can select them when I want them. But I couldn't believe it. I could not believe it. Day. Okay. So quick. Oh, that's so awesome, Dan. That'd be great. Definitely. Join in. Are you going to take 320? If you're watching right now, you're watching 320. This is just y tilde x comma data equals, and this is the name of the data frame. So that's the code right there. You just put in this is your y variable, these are your x variables, comma data equals. And so you just fill it out with your data, your x variables you want, and your y variable, and you make a model. And you can take a look at that model. Here's the summary of the model. And what do you notice, Tingying, what do you notice about the coefficients right there? Awesome. Yeah. I would like to do finite math with R. I like doing everything in R. What do you notice about all these coefficients right here, Tingyang? I'm like so, I don't know, just sore and tired today. What do you notice about all the coefficients? All the coefficients are what? It's going to be a trick here. Trick is coming up. All the coefficients are what? Every single coefficient except one, technically. Every single coefficient except one is what? All the coefficients save one are all what? Okay, in the intercept. Okay, no one cares about the intercept, though. Just talking to myself. Mubot, are you here? Oh, Mubot is here. All the coefficients except one are what? All the coefficients for the x's in the model are balls help falls. You got that, Mubot. So when you look at all of these right here, all of these coefficients are what? Negative. Exactly. Great job right there, Dan. Yep. And so here's the thing. And yet a lot of them are not statistically significant either. Here's the thing, though. When we look at our model, so you remember regression, Dan, I'm sure. Check this out. Here is regression with indicator variables. Looks like funfetti. So here is a regression with indicator variables. Now, what do you think, since the coefficients are negative, what do you think is going on right here? And you see there's Friday. What do you think it means since all the coefficients are negative? And Ting Yang can probably explain this. Since all the coefficients are negative, that means 2 days that are otherwise identical in their effective average temperature. We'd expect the days with what? To what? What is going on right here? What does it mean that these have negative coefficients for each of the days? It's their what from what. The negative coefficients are their what's from what. And this kind of answers the whole question, especially when you see the visualization right here and you realize that, awesome, Kiana, we're covering some 320 right now. Ask those questions. It's that Tennessee weather. I love that right there. So all the days of the week, Kiana, have negative coefficients. We just observed that. Every day of the week has a negative coefficient. What does that mean, that every day of the week has a negative coefficient? Every day of the week has a negative coefficient. Interestingly enough, one of the days of the week isn't showing up in the output. I don't know what day of the week it is, but one of the days of the week is not showing up in the output. And that's kind of a very important thing. So when you look at it, one of these days is not showing up in this output over here. Yes, Keon is 100% on track right there. Every day of the week is expected to have a lower demand than the reference level, which is Friday. And think about this. Yes, it's Mary. Great job, Mary, also right there. We'd say 2 days that are otherwise identical, but one day is a Saturday and the other day is a Friday. The day that is a Saturday is expected to have demand that is 121.179 bikes lower than Friday. So it kind of makes sense that Fridays are the big biking day, apparently. Maybe we'll bike to work on Friday, but these are kiosks from, I think, the Washington, D.C. area where people can rent bikes. But Fridays are the big demand day. And you notice right here that every day has a lower demand than Friday when you do otherwise identical effective temperatures. So you just see differences in the intercepts of the line, which is how we get these indicator variables right here. They can only become zeros or ones. So what other, keep asking questions. That pretty much does D2. What day looks to have the highest and lowest? I'll let you kind of decide. Take a look. You can look at it mathematically, or you can look at it visually. You bet. We're going to do a ton. We're going to do that here. I'm going to let 320 have at least another 5-6 minutes at least. We'll see if they what questions are there? What shall we talk about? And then Charlie, you bet we're going to do another chapter 16 quiz question. We've even got some chapter 17 coming up. Ooh, chapter 17. What else, 320? What are you thinking? Can you be a researcher? Yeah, totally. Is that 17, Gigi? Did you say that's chapter 17? Is it quiz or homework? Chapter 17. So this should make the model. I think maybe 320 is good right now. We'll find out. Chapter 16 homework. Chapter 16 homework. Question 2, part C. Let's go look at that. Thank you so much. Dariana, thank you so much. Let's make you a mod right here. You bet. Let's do 2C. Let's take a look at 2C. Which part of 2C? So let us compare the average demand for rainy and non-rainy days after accounting for the temperature. Fit a regression model predicting demand from these right here. So we're going to do the same sort of thing. When we fit our model, we store into M. We can call it different things. This is just a name. You can just put any numbers what you want on it. You can call it like MC for the model name. And then let's go here. D1, is it, we have 6 indicators. I think you do. Yep. 1, 2, 3, 4, 5, 6. 6 indicators. Yep. And LM. And so what's the variables? We're predicting demand. And we're doing it from effective temperature and weather. And I don't think we're doing an interaction. Please correct me if I make a mistake. Like if I don't see an interaction or something like that. And then we do data equals EX5 bike. And we're good. Go away. There you go. Fit a regression model predicting. Examine the results of summary as well as visualized model. Use the regression model to answer below. Okay, so summary, MC, visualize model, MC. There we go. Among days, how do we tell which level of days does not have an indicator named after it? Okay, so to Ting Yang's question, one of these is not showing up in my model right now. One of these is not showing up in my model. So Ting Yang, which one of these, this is not the day question, but which one of these is not showing up in my model right here? Which one of these is not showing up in my model? It looks complicated, but it gets easier, Dan. Like you make them in RStudio, and when you're done with it, you can knit it. So you can actually knit it to a file. So once you're done, you just go up here to knit, and it turns it into a file for you. And so it's like Kiana and others. Do you think it seems complicated at first, maybe, but then does it start to get pretty easier? Like when you make it, I think you're on the right track, Ting Yang. Yep, you got it. When you saw this, when you're like, oh, no rain is not showing up right here, and it's the reference level will be the one that does not have an indicator. Kiana, excellent work right there. Kiana's right on track. The reference level does not have an indicator. It gets a lot easier. Everyone says like the coding is like the scariest thing, and by the end you're like, you just type the code and you just it's like knitting at first was scary, but now it's super easy. Exactly. It's one of those things. By the end of the semester, you're like, yeah, it's not that bad. You're like, it's just a little learning curve at the start. I'm always like, semesters I don't teach 320, I get scared. I had a question about the implicit regression equation on 2 part C. Yeah, let's write out the implicit regression equation. So when we write out the implicit regression equation, we can actually write an equation the following way. Check this out. Anything you write in here now goes into an equation. So you can literally do things. I think this is how you do it. You can do sigma. No, wrong slash. You do that, and there's sigma. You can do things like mu, and it starts putting them in. So we're not going to do that. Here's what we're going to do. When we write out our regression equation, let's talk about the regression equation right here. The regression equation is y hat equals b0 plus b1 x1 ... plus bk xk. Now all this means right here is we just continue through putting all the coefficients next to the x's. This is the predicted value, this is the intercept, this is the coefficient of the first x, all the way to the coefficient of the last x. And you just do this kind of algorithmically. You just go through and you go here, you put your pen down, and you put the intercept, or you go first, you say we're predicting demand, and then we go here, we put this, then we take the coefficient here, this is B1, we times it by the x value, and then you go plus, or it needs to be minus technically, and then you go here, and you times that by the x value. So this has got it. There is our full regression equation, but we're not done yet. But wait, there's more. Because when we write this out right here, this is the overall regression equation. What are the only values weather rain can take on? This will basically answer the rest of the question. What are the only values weather rain can take on? Weather rain is an indicator variable. And just look at how the equation looks. There's one of the values right there. Yep. Weather rain can only take on 0 or 1. Because if we put in a 1 here, then it'll be raining. If we put in a 0 here, it'll be not raining. So it can only be 0 or 1. So I'm not going to solve out the full thing, but make sure to put this in and reduce. If you were to go right here and put in a 0, then you're saying it is not raining. If you put in a 1, then you're saying it's raining. And that'll only cause, if you solve out the equation, this change to it will only be a change in the what of the model. If you reduce the equation, this change will only cause a change or create a change in the what value of the model if you reduce everything. If you reduce everything down, this will only create a change in the what of the implicit lines. And you should reduce it. You should show it mathematically reduced. Boom, right there. Kiana gets it, and you can see it. Because when you add when you add this, you'll only get a change to the intercept right here. Or subtract. It is subtract. It'll only cause a change to the intercept. Because I was like, that's the reference. And then we're so, yeah. That's the difference. This literal difference right here is 656. Like, it's like, how far is the black line away from the red line? 656. That is their difference, and they're parallel because they both have the same slope. So does that help right there? Does that make sense, Dariana? So does that make sense on how to do this? I basically I didn't write the 2 lines, but from here, I think hopefully it makes sense. And also it makes sense how I went and took y value, intercept, and then plus this times this, plus this times this. And it wasn't this question, it was the second one. Oh, wait, C2? Is it this one? Compare the differences in the averages from A to C if they're more than 10%. Oh, wait. What is the implicit regression equation? Sales to ads for the last... Oh, it's at the bottom. It's at the bottom. And then we'll do that one right there. And then we'll hop to some 201. So for this one, you have to take a look at what we have right here. And you have to compare it to the first value. I'm going to put some question marks here because I don't want to show it. But if you do this right here, if you take our current coefficient right here and you compare it to what we found earlier on back here we are. If you compare it to what we found back here, which I won't show it, I just want people to find it. If you compare it to what we found via this code and look at the difference in the values, then you can compare and ask, like what percent of it is it? And is it more than a 15% change? Does that make sense? You want to look at this compared to the first value and say, is this more than a 15% difference from what we originally had with the original value? So, and then what is the implicit regression equation sales to ads for large products that go in the bedroom? This is going to be very, very similar. Great question right there. And what we need to do, and what I would do, is sometimes writing things out can really help. So we'll do this one right here. Let's just show. What I would do is I would take, and we're trying to do sales equals this plus this times this plus, so it's a minus, this times this minus this times this. You just got to algorithmically go through, just step by step. This times this. There we go. And here is the full equation. And now you have to be careful. So when we decide what's a 0 and 1, the question right here was, we have something for large products that go in the bedroom. So what should we put in for size small? What should we put in for size small? We'll do this. What should we put in for size small? A 0, exactly. And what should we put in for room office and room kitchen? So for size small, we should put in a 0 because it's a large product. It's a bedroom product, so what should I put in for these? Because it's a bedroom product. Does that make sense right there? Since it's a bedroom product, it does not go in the kitchen, it does not go in the office. And so there we have it right there. And we should be pretty good. I mean, these are all zeros. They're all being multiplied by zeros. So does that make sense right here? Does it make sense, like kind of what's going on right there, and how we can, and then reduce it? Don't show this. Like, I'm kind of half working these right now. I'm kind of getting the ball rolling to be like, here's what I would do. I'd write this out, and then I'd put in these numbers and then solve them. And once you do it a few times, it's like, oh, you just write the equation, then you put in your zeros and ones to solve for whatever the indicators are, if the indicators are on or the indicators are off. Great job, Dariana. Great to have you here. Keep asking those questions. I want to hop back to some 201 right now, but that's what we like to do. We answer questions. We get work done. We did this earlier today. Maybe take a screenshot of this if you want. 320 if you're here. We should show this in class at 150. But we wrote this out this morning. Oh, man, up early. Oh, man, yeah, it's like Tuesdays and Thursdays are so killer this semester. Oh, man. Oh, man. Oh, geez. Oh, geez, bro. We're doing... just going to do random horrible Morty impressions. I don't know. Just felt inspired. What was the question we had here? The question was, here we go, the scanners. Yeah, let's do the scanners. Okay. So this one right here works really well if we do it visually. So let's go ahead and grab this question and visually talk about this 201 question. And what we're going to do is we're going to look at it visually speaking. And here we go. So what do we have? A researcher developed scanners for hidden weapons at airports, has concluded that a new weapon scanner is significantly better than the current scanner, and they made their decision at the 0.025 alpha level. So what does alpha mean? What is the whole point of alpha? What is the point of alpha? What is the point? Why do we have alpha? Alpha tells us at what point we can do what. What is the point of alpha? What is the point? Reject or fail to reject. Exactly. Alpha tells us when we can reject or fail to reject the null hypothesis based on the p-value. Exactly. So if the p-value is less than alpha, we can reject the null. If the p-value is more than alpha, we will fail to reject the null. So the region down there is the fail to reject. The region up here is the fail to reject. And the region down there is the reject region. So that's the rejection region. This is the failure to reject region. And so what we notice right here is that they were able to reject the null. And that means the p-value must be somewhere in here. So the p-value must be there. Nice job, Charlie, right there. If it's high, just let it fly. That's the let it fly range. That's the reject the null range. When the p-value is high, just let it fly. What do we mean? Higher than alpha. So would they have made the same decision if they put their alpha level all the way up here at an alpha level equal to 0.20? Would they have made the same decision? We know that their p-value has to be less than the alpha of 0.025. We know this because they told us they rejected the null at the 0.025 level. Would they make the same decision up here? If they put their alpha up here and change it, so they'd be doing this then. So here's what they'd be doing. They'd have a rejection region that looks like this now. They'd have this rejection region, and they would have this right here as a non-rejection. So wait a minute. We know the p-value is down here. We know the p-value must be less than 0.025. So would they still reject at the 0.20 alpha? So with the 0.20 alpha, we know the p-value is less than it because it has to be less than this. Does that make sense? And then we've got the other one right here. So now we've got the last one, the 0.001. So now we're saying all the way down here, and we'll put a little alpha right here at 0.0001. And now the rejection region is going to be this little sliver, which I'm going to barely see it. So that little sliver is the rejection region, and this right here is the not rejection region. So now, if you look at this, could they reject? Possibly. Could their p-value be less than this? Possibly. Their p-value could also be more than. You might say, I think you don't know. It's frankly, you don't know at this point. So at this point, we don't know what they would decide. Would they reject the null? It's possible. Very hard, but yes, because it's a very low alpha. Yeah, the lower you make alpha, the harder it is to reject. And this would have less type 1 errors because alpha is type 1 errors. So with this right here, we don't know what they would decide at the 0.001 alpha level. So they would have been the same, and it may have been different at the 0.001. So they would still reject the null. And I think that's got it. That's a good tricky one. People might just start guessing that one has to be a good scanner. Exactly. Yeah, that's what they're saying. If they use a 0.001 alpha, then they're requiring more evidence. They're saying we need a lot of evidence. So the 0.001 alpha is a very stringent test that's saying we need a lot of evidence. What other questions are there? I really like this question. I've done that visual before, if you can't tell. I think that's a really, really good question right there. We did these other ones yesterday. We did the suing discrimination. So if you're watching this video right now, look to yesterday's office hours. We might circle back and do these. We've got 23 more minutes. I'm just going to play with my hair while I still have it. While I still can, I don't know, long hair. What was the other ones? Let's look at the other questions people had. I like what Kiana said. Also, coding has gotten a lot easier. It's really cool to think back to September when I had no clue what I was doing. Now most code is easy. Yeah, Kiana, that's so awesome. I'm really proud of you, Kiana. When you look back like 2-3 months and you're like, I had no idea what I was doing. One really quick story while people say, here we go, we got a good question right here. Before lending someone money, yeah, I think that's the, oh no, wait. Let me pull that up right here. Before lending someone money. And I'll talk about this little aside while I pull it up, and then I'll look back on chat here in a second. Students have taken 320 and 474, and one student said that her father was hiring someone to do code, and the guy really he'd been coding for over a year, and she had only been doing code for like 2 months, and she said his coding skills were not as good as hers. She was like, he doesn't know how to do for loops, he doesn't know how to write functions. And it was in the summer when I teach 324, 74 back to back. But she was like, yeah, he's been coding for a year and he really doesn't know the things that I know. And I was like, that's because we try to push our students. We're trying to, get you to learn, there's a difference between learning something yourself and being like pushed to learn it in a class. Because we have faith in what we do. Oh, can we go over, which one was it? Can you do a question that says, define the parameter and write the null alternative in terms of the parameter value? Yeah, sure. Yeah, definitely. Let's definitely do that. And then Gigi wants the before lending someone money. You got it. Here we go. So let's talk about before lending someone money. Bank is going to use a point strategy. So what it is if the people have enough points, then the bank says they're good to lend money to. Now, as this problem lays out, the bank is going to assume that they should lend people money. So the null hypothesis for this bank is going to be lend money. So the null hypothesis is lend money. Null hypothesis, lend. Alternative hypothesis, don't lend. Now, let's be very clear. What is a type 1 error? What is a type 1 error? I want to put this right here next to me. Oh, it's going to go. There we go. What is a type 1 error? In a type 1 error, the null is what? In a type 1 error, the null is what? In a type 1 error, the null is what? Error is made when a false null is not rejected. Exactly. So we'll note, like Charlie got it in the inside thing. Sorry, my brain's just breaking. So many trues and falses. Exactly, Gigi, you got it. You just mess with me. You see him? Does Brian know this? I'm going to make sure Brian knows it. Gigi, great job right there. 1,000 points, Gigi. So in a type 1 error, the null is what? In a type 1 error, the null is what? So how we practice. Type 1 error, the null is true, and we reject it. So we're going to reject the null right here. In a type 1, the null is true. This is 1, and this is a t. And we go right here, we reject this, and we have evidence for the alternative thus. So in a type 1 error, we reject that we should lend money, and we don't lend money to someone. So we say, we shouldn't lend the money, even though, and you got it, Meryl, we'll definitely do some chapter 17. I'll make sure we last 10 minutes, so we go do that. And in a type 2 error, the null is false, and we fail to reject it. That means the alternative is true, but we are going to fail to reject the null, which means we're going to still believe it, and the null is false. So what does this mean if the null is false, but we continue to believe it? If the null, you're welcome, Meryl, you got it. Appreciate all the hard work, everybody. If the null is false and we fail to reject it, what does this mean? We're going to do what where what is true? We're going to lend someone money where we shouldn't because the null is false, but we fail to reject it. This is the type 2 error. The null is false and we fail to reject it. So in the type 2 error, we have that the person should not have money lent to them, but we fail to reject that, so that is not good. So a type 2 error, when a person defaults on a loan, is a type 2, and the type 1 is when the bank misses the opportunity. Suppose the bank decides to lower the cutoff, so now we're making it easier to loan money. So when you think about this, if we make it easier to loan money, will we reject the null more or less? If we make it easier to lend money, will we reject the null more or less? If we make it easier to lend money, will we reject the null more or less? If it is easier to lend money, exactly less. So if we reject the null less, is that a higher or lower alpha? If we reject the null less, is that a higher or lower alpha? When you say you're going to reject the null less, that would be the same as doing a what? A lower alpha. Because alpha is how often you reject the null due to random chance, a type 1 error rate. And so if we make it easier to lend money, we will reject the null less. Exactly. It's harder to reject because of the lower alpha. Perfect knowledge right there, Charlie. What does this change in the cutoff value of the chance of error? So think about this. If we're making alpha lower, alpha is literally connected to what? We'll do one of our classic memorization things right here that we need to know. We need to know 1, 2, A, B, positive, negative. Exactly. And so if we make alpha lower, what will that change? Type 1 error will go what? Type 1 error will go what? If we lower alpha, it's directly connected to type 1 error rate. So type 1 error rate will go down. Lower alpha literally equals type 1 error. And so decrease in type 1 and increase in type 2. That should be right. Yeah, I get so scared. Exactly. Lower alpha lowers if alpha is lowered because alpha literally is type 1 error rate. So type 1 error rate is alpha, type 2 error rate is beta, and they are inversely related. They are not complements. They're not complements. And Charlie wanted another one. Charlie said, define the parameter. Let's look at that one. Define the parameter. Define the parameter. Load. So what's the name of the difference between those? Effect size. I was like, we just clear these. Clear these questions. Threshold, that's alpha level. It's hard to find the answer. Like I know the answer and it's just hard to find it. Can the question, which of the following is true? Yeah, let's go look at that one. We'll do Charlie's, then we'll do that one. Then we're gonna do Meryl's question. You got it. What is probability that we correctly reject the false null? That's the power of a test. These are just good review questions. Just make sure you know the terminology. When a false null is not rejected, that's the false and fail to reject the false null. It's type 2. True null rejected. We shouldn't reject true null. And where is it? Is it this one right here, Charlie? We might have to circle back. We did this one at the very start. I think this was the first one we did here, Charlie. Was this the one you're looking for? I'll circle back, Charlie. We're gonna do Gigi's, then we're gonna do Meryl's, and then but don't worry, you didn't know that. Don't worry about it. We'll circle back. So rewind the video a little bit to the start, and you'll see me answering this, and you'll see how we have to first identify if this is categorical. Let's see if there's a new one on here we didn't do before. I think they're all the same. So if you notice, some of them are categorical. If they're categorical, we'll use P. If they're quantitative, we'll use mu. Whatever we put for this slot right here, we have to put for all of them. So if we put P for a slot, we'll put P, and then the null always has the equal sign. When we're asking if something is going to have a lower, we're doing less than, and these will be means, and these will be proportions right here. So when you do this, P is when we're testing the true proportion, mu is when we're testing the true mean, and the null always has the equal sign. So if you get this question, you can always put your equal signs in here, and then if you're doing P, it's the true proportion, and mu is the true mean. Hopefully I don't make an error. There's so many slots to fill out that it's like, don't want to make an error. And has it, is it, Bank wants to know if the percentage has decreased. So decreased, wants to know if it's decreased. And is this the same? I think we've done it. Hopefully I didn't make an error. Woo! Got scared there. Got scared. We made an error right there. And I think Gigi had one on this one. Charlie, we'll circle back and we'll talk more on this if you want. And Gigi wants the one. Which of the following are true? Briefly explain. Which of the following are true? Cool. Okay, we got this. Well, let's go take a look. And here we go. And let's take a look right here. Okay. Using an alpha level of 0.05, a p-value of 0.01 results in rejecting the null. Does that sound true or false to you, Gigi? Does this sound true or false? Using an alpha of 0.05 and a p-value of 0.01. So remember, alpha is the point at which we reject. So this would look something like this right here. It's saying if you use an alpha equal to 0.05 and you have a p-value equal to 0.01, you would reject the null. That is very true. The alpha level depends on the sample size. Here's how we pick our alpha level. We usually use 0.05. Have we ever talked about, we have a sample size of this, let's use an alpha of this? Have we ever been like, our sample size is this, so let's use an alpha of this? Have we ever done anything like that? Have you ever said, here's my sample size, here's my relative alpha, or let's use an alpha for this sample size or a sample size for this alpha? This is as false can get. You just pick your alpha, and usually alpha is 0.05 by default. With an alpha of 0.01 and a p-value of 0.09 results in rejecting the null. So what do you notice about this? If we have an alpha of 0.01 and we have a p-value of 0.09, what would you notice right here, Gigi? What do you notice about this? It says it results in rejecting the null. So if we have an alpha of 0.01 and a p-value of 0.09, it says there you reject the null. Is that true or false, and why? So with an alpha of 0.01 and a p-value of 0.09, this results in rejecting the null. What do you think about that? Thoughts on this, on C right now? Would that result in rejecting the null? That is definitely false. And why is it false? Because let it fly, exactly. Let the null fly. That's false because the p-value is above alpha. If the p-value is above alpha, just let it fly. With an alpha of 0.05 and a p-value of 0.07 means the null hypothesis. Have you ever heard us say anything like this? Have you ever heard us say the null hypothesis is true? Have you ever heard us go into like the null hypothesis is true? With an alpha of this and a p-value of this, the null hypothesis is true. So it's saying with an alpha of this and a p-value of this, that means the null was true. Have you ever heard us use that sort of terminology? With an alpha of this and a p-value of this, the null hypothesis is true. We never say this. We would say we do not reject the null, or we fail to reject the null. We do not have sufficient evidence. So in this instance, we are going to fail to reject the null. We do not have sufficient evidence to show that there is a difference right here, or that there, whatever we're trying to show. So in this instance, we fail to reject the null because the p-value is high. We just let it fly. And that should do it. We should be able to go through and answer these questions. So this statement was true. Choose the answer below. This statement is false because only a p-value, or they're set independently of each other. So we set those independently. Choose right here because only a p-value less than alpha results in rejecting the null. Choose the correct answer. The statement is false because a p-value greater than alpha only indicates there is not enough evidence. And that should do it. We got it. Does that make more sense, Gigi, as we go through and kind of talk about why each one is false? And then we kind of look at their answers too, but we can try to understand, like, what would we actually do here? Awesome, Gigi. Excellent work. Good practice. Make sure you understand when the p-value is high. Just let it fly. Let that null be. Fail to reject. That is key. Let's look at Meryl's question. And then, Charlie, we still got enough time, Charlie, to circle back. If you're wondering about that one still, Charlie might be watching that part of the video right now. We still have enough time to circle back. And let's see here. Meryl, which one is it again? You're probably putting in the chat again, or I'll scroll up here in a second. So chapter 17, comparing two means. We're almost done with assignments. The question Meryl has is commute and sugar content. Okay, we definitely got, okay, the commute one, it's not so bad. The commute one, oh, is it the homework? It's homework. Let me do the homework. Okay. The commute one you have to do the equation on. And I can't think of the sugar content ones. Oh, is it the cereal? Is it the adult and children's cereal one? It's funny, that's the way I remember it. It's the adult and children's cereal. Okay. Hot dog one's easier. Okay, that's standardized test scores, and here we go. So with this question right here, we got enough time to do this one probably. We're good on this. Okay, we don't need the last part. This one is a notation one. This is notation, 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 notation. So let's go ahead and take this over to our notation sheet and start filling out all the notation. So I need some help, everybody. I need your help for this. Let's start talking about notation right here. The commute, you got it. And I need to know what we have right here. What we have right here. I think that's everything. So there's everything we need, and this problem has another thing you have to get in a moment. But while you put some stuff in chat right here, start labeling things. And you notice I put 2 arrows on this, but start labeling stuff. Oh, look at that. I'm already there. Okay, so start labeling stuff. What do we have here? We need to start figuring out the notation for this. And I'll start writing the equation to help you out. So see if you can recognize any of the notation right here. You're really close, Charlie. You're really close. Charlie, you're super duper duper close. And I think Charlie got the question figured out. Great job, Charlie. You're super close. And this will slowly give you a hint right here. Remember, this is a 2-sample t-test. And Charlie, you're right on the track with that. So this will be sample mean, and these will be sample means. These will be sample mean for route A. That's sample mean route A. And this is sample mean route B. And then what else do we have? So think about how I said, I was like, you're kind of close with n equals 15. And it is cool. Exactly, it's y bar because it's a sample mean. Exactly, because these are taken from a sample. It's not the true mean. So we were investigating the true mean. We're trying to estimate what the true difference is between We're trying to estimate this difference between the 2 routes, the true difference between route B and route A, and how long they take. So we're still missing a bunch of notation right here. We have 4 things that we're missing, not including t. I'll find t once we do this right here. Let me put in the chat. To find t, we're gonna need to go to this side right here, and we're gonna need these other things. This is actually everything we're missing. I think was it. Yep, and let's see here. Yep, and that's gonna be the degrees of freedom. So I'm gonna round that to 23. So as Charlie points out right here, this is standard deviation of route B. So no, that's standard deviation of route A. Standard deviation of route A. Standard deviation of route B, and this is going to be N1 or NA and NB, because that's the sample size for route A, and the sample, it says he rides each route 15 times, so that's the sample size for route A and the sample size for route B. Does that make sense, Charlie and Meryl? And that is the sample size for each route. So now we need to take the difference between the routes, which will be 44 minus 42. We're going to go find that t statistic in a second. And then we're going to go here and do 5 squared over 15 plus 3 squared over 15. And then we have to go take, exactly, it's sample size 1, sample size 2, bingo. Then we're going to take the degrees of freedom we calculated. I put this in the chat, but there's sample size 1, sample size 2, standard deviation 1, standard deviation 2. We take the degrees of freedom. We go over here to our applet. We put in the degrees of freedom. We put this inside of here, and is this the t-score we need? This is a 95. Was it 95? 2.74. Let me see if this changes it slightly. Really? Oh, I don't like that. I'm going to use this. I'm going to round it up. This applet, you need to round sometimes. Some applets don't do rounding. I'm going to round this up. Let's see if it does it without the rounding. Wow. Will it work without the rounding? If I get this wrong, it's because of the rounding. 2.074. Okay, let's, against my better judgment, and when I get it wrong, I'm just going to be like, I told you. 2.074. There we go. So that's when I put it in without the rounding. We'll check in a moment here. The margin of error is probably going to give it to me. So that's 25, that's 9, that's 24, 15 divided by 24. That's 9, that's 1.6, right? 1.6? So 1. No, what am I doing in my brain? 34, that's... Oh my gosh. Should be 2.1... Oh my gosh. Let's just do this. 34 divided by 25. 2.166? Oh my gosh. What am I doing? Oh, 34 divided by... There we go. 2.2666. Okay, I got it. My brain just couldn't do math today. I did fractions earlier. Now I can't do them today. We need to square root this. Square root before we forget. We're just solving the inside of this. We need to times this by 2.074. There we go. And we just have 2 plus or minus this. As long as our decimals are correct, 3.11225. There we go. I think it has the leeway on here that should give it to us. So let's go back and look at the question. And we're going to make the confidence interval. So remember, it's 2 plus or minus this. So 2 minus this, negative 1.12, negative 1.12, and then 2 plus this, which is just going to be 5.12, and 5.12. We check our answer, and it did have enough leeway in there. So it did give it to us. Should we believe the claim of 5 minutes? Should we believe the claim of 5 minutes? Yes or no? Do you think the difference between these routes might be 5 minutes? Yes or no? Should we believe this claim? Yes or no? We'll do the next question here. We'll do the sugar content. Should we believe this claim of 5 minutes? Yes, because it is contained in the interval, which means we would not reject it. Yes. Sugar content of cereals. This is a jump question. This one's much easier with jump. Watch the steps. We're going to go here to copy to clipboard. We're going to copy the data. I'm copying the data multiple times. And then we're going to go here to a jump workbook. Go to File. Go to New. Go to Data Table. File, New, Data Table. Now we're going to go to Edit. Paste with column names. When we paste with column names, it'll put it up here, and we'll have 2 quantitative columns. If you do this, restart, restart. If you see this, exit out and restart. Don't try to fix it. There's a way to fix it. Way more complicated. Make sure when you pasted with column names. We're going to go here. We're going to go to tables. We're going to go to stack. This is tables stack. We're going to double click children's cereal. We're going to double click adult cereal, and we're going to click OK. Now that we're right here, maybe you can pause this video later on, or you can rewind right now. Now that we have all the data in here, you can see we have the label. You can call this like cereal type if you want. You can call this sugar. You don't need to change these. This is just going to make it look nicer. Now that we have everything ready to go right here, let's go to Analyze and fit Y by X. I think there is a way to do an Excel. Probably with the data tool pack, you can do it in Excel. There's a lot, you can do a lot in Excel. But here you go. Once you go here and go to t-test, there you go. We have now done it. We have made our interval. This right here goes from 31.21 to 39.5, and this is our interval. What is 35.36 divided by 2.0579? I'm going to do it in my head right now. You ready? 17.18281. Because all we need to do right here is understand that this t ratio is just these two numbers divided. So the t ratio, if we divide these two numbers, it might have more decimals we don't see in the background, is just these two numbers divided. This number by this number is the t ratio for the test. So everything right here looks really excellent. We've got the problem done. 31.21 and 31.21 and 39.51. And let's go right here. 39.51, 31.21, got it. And interpret the difference. So I am 95% confident the true difference between adult contents in sugar content in cereal and children contents in cereal is contained in the interval 31.21 to 39.51, with children's cereal having more sugar in it. So we have here more grams than children's cereal. Children's cereal has more than adult cereals. So let's go ahead and put the lower bound here of 31.21 and 39.51. Check our answers. We did put in the right spots. And we did it. We started 2 minutes late and we end 2 minutes late. So in context, this means that children's cereals on average, we would expect them to have between 31.21 to 39.51 more grams of sugar than adults cereal. Does that make sense, Charlie? On average, we would expect to see 95% of the time that the mean for children's cereal is contained, the difference. Last question, if the p-value is smaller than the level of significance, what conclusion should we reach? So if the p-value is lower than alpha, what should we do? If the p-value is lower than alpha, what should we do? You got it. Nice job, GG. You got it. You don't doubt yourself. You got this. Like when the p-value is lower than alpha, reject the null. When the p-value is low, reject the null. When the p-value is low, reject the null. Lower than alpha. That's the level of significance. Alpha is just at what point are we going to reject, and that's called the significance level. So much like terminology, right? Like why don't we just call it alpha or just the rejection rate, or like, why is it also called the significance level? I thought you said yesterday during class the t-ratio is like the difference of something like that. Yeah, the t-ratio, and very good note right there. The t-ratio is going to be the ratio of the difference to the standard error difference right here. So this is the t-ratio, which is not the same as the t we use for the confidence interval. So this t-ratio right here is actually the t-test. So does that make sense, Charlie? The t-ratio right here is the t-test. So the difference divided by the standard error, the difference is the t-test right there. So would what I said about in the chat be correct? So in context, this means that children serial. Oh no. So no, this it wouldn't be how many times more. It's kind of a standardized difference. Oh, I see what you're saying right there about the 17. That means it's like a standardization of the difference. So it's how many standard errors it is away. So we expect to see a difference of 0. If you look at this graphic right here, we expect to see a difference of 0. We observed a difference of 35, which is 17 standardized units away. Oh, you can't see it off the edge there. So the 35 right here is 17 standardized units away. So this right here, this t-ratio is how many, it's like a z-score basically. That's the best way to think of it. It's how many standard errors it is away from 0. So this is 17 standard errors away from 0, which is it's ridiculous. It's off the curve. The difference. So it wouldn't be versus adults, the difference we observe between the serials is 17 standard errors 17 standard errors away from 0. Oh yeah, it's ridiculous. Oh yeah, great. Yeah, it's super significant because it's way off the curve. So do you think, let me ask you this, Charlie. Do you think the differences in sugar content for children's cereals versus adult cereals is by random chance? Do you think the differences in sugar content for children's cereals versus adult cereals is just due to random chance? And then look at this right here. Do you think it's due to random chance, the differences that we observe? Exactly, hence the p-value. And then what do you think? Because what's that p-value telling you for the differences being due to random chance, for the differences between, oh, I don't think they're due to random chance at all. And you can see it in the data that children's cereal are all up here and adult cereals are way down here. So no way. These differences are not due to random chance. Children's cereals definitely, we're about as certain can be that the average children's cereal has way more sugar than the adult cereals. And we're 95% confident that this difference in sugar contents between the children's cereals and adult cereals is contained in the interval 31.21 to 39.5. So does it make a little more sense when you realize here we're trying to estimate what's the true difference between, if you took all adult cereals and all children's cereals, what is the true difference between their sugar contents for all the cereals? Yep. And then we estimate the true difference is somewhere between 31 to 39. Every kid cereal I see is a cereal version of candy. Well, that's why I eat them. I had my Lucky Charms this morning. I mean, come on. What else? I bought they have this huge box of Lucky Charms at H-E-B. H-E-B, good grocery store. We could use an H-E-B in Knoxville. That's what I'll say. I'll bring an H-E-B back to Knoxville with me. It's kind of like a Trader Joe's / Walmart. It's as big as Walmart and has as much choices as Walmart, but it has local stuff too. So H-E-B, I'm telling you, go to Knoxville. We'll have an H-E-B in Knoxville, even though it's like H-E-B I think is a Texas thing only. You're like, nope, we're Texas only. Well, okay, it's the good part of Texas. Oh man, who'd have thought I lived in Texas once before. Who'd have thought? And if it's negative, it's to the left. Yeah, exactly. If it's negative, that would mean that the adults had a higher sugar content. If it's negative when standardized. Yep. So just because the standard error can't be negative. So if the difference is negative, then the adult cereal was the higher one. But it's positive because children's cereal is higher. Since children's cereal is higher and we're doing children minus adult. And JUMP always uses reverse alphabetical order. I think that's got it. Great job, Charlie. Great questions. Making sense of this output's what's important. I'm going to go take a nap. Oh, man. We only have like 2 more days of early wake up. Could we actually claim this is a fact? We can't say it's a fact. We just say we have very good evidence. The smaller the p-value, the more evidence you have. And this is a ton of evidence. I mean, you can say it's like, if someone told you, like, no, I don't think there's a difference, you'd be like, there is so much evidence to support this. I mean, because we haven't looked at all serials. We would just say there's ridiculous evidence. Like, the differences we would observe would only occur about 1 in a quadrillion times if there really is no difference. If there really is no difference, and I'm saying because e to the negative 21, if there really was no difference between these, we would only observe something like this one. Is that like climate change? Oh man, that's a do I have the climate change data on this computer? Do I have it? Let me see here. I don't think I have it on here. I don't think it's my temperature data. No, this is not temp data. I'll have to see if I have my climate change data on here. I have climate change data, but I might have to go recreate the data set again just because it's on my laptop. I should get it on my laptop. Like, we can't claim it's real, but there is. So with climate change, yeah, it's the thing is like, one thing people used to do is, we'll talk about this because it's the power of the test. Well, actually, we just talked about this in 201. So I'll mention this real briefly here. If you take your data and you take, we used to hear this all the time. We have data going back, I think, from about 1897 or so up to the year 2020 on climate change. If you go here and only take the last 7 years of data or so, what have you made very small? If you only take the last 7 years of data, Charlie, what are you doing? And you used to see this all the time. Or people would use like the last 13 years. People would do things like the last 13 years or the last 7 years. What are you making very small by taking only the last 13 or the last 7? This is what I call an abuse of statistics. It happens all the time. But by taking only the last 13 or last 7 or so, if you take only the last 13 or last 7 years, what are you making very small? You're making your sample size very small. So if you go and people would say things like, there's been no significant warming for the last 13 years, and you will literally see data that looks like this, where it's going up or something, it'll have an upward trend, but it won't be significant enough. And the thing is with a small sample size, what are you lacking? If your sample size is small, what have you decreased? If your sample size is small, what have you decreased? So you make small sample size. With a small sample size, you will increase your type 2 error rate. So if your sample size goes down, then your type 2 error rate goes up and your power goes down. So what they're doing right here, and they're not wrong. You can say there's been no significant warming over the last 13 years, but with a small sample size, it would be very hard to detect. If you go to and look at the whole sample, you can say over the last 100 years, there's been significant warming. But when you have a very small sample size, you're unable to find results because of lack of statistical power. So I'd always see people reporting in the news at different intervals. They'd be like, there's no significant warming over the last 8 years. And I'm like, well, because you're using a sample size of 8. And when you have a really small sample size, your type 2 error rate goes way up and your power goes way down. So it's kind of a trick people use for statistics to be like, oh, there's been none of this over the last, like very small sample. But wouldn't your confidence be lower too? Because so if you were to make a confidence interval, so this actually does relate to confidence intervals, to estimate the coefficient of this right here, which would actually be relative. Let me look that up. I don't do this equation so much. 2 seconds. I should know this equation off the top of my head. Standard error of slope equation. What is the equation for the standard error of the slope? Some stats person is like, how do you not know that? Is that really it? Oh, there it is right there. No wonder I never solved that. So here's one person's interpretation of it. So here's the standard error of the slope. Let me go. Where'd it go? I never solved this equation by hand. So it's sum of the actuals minus the predicted squared. So it's the residual squared minus the distances from the... Okay. Interesting equation. It's the first time I looked at this equation in like years. Okay. So here we go, Charlie. Let me put this in here. So if you were to make a regression equation, let's edit this. Picture format, crop. That's why I do not solve that one by hand. And when you make a regression equation, I want you to think about this. Sorry, I can't see the screen now. No, really? There we go. Wait. Okay, cool. The regression equation, let me bring back up the chat. Can we do the recent poll on this quiz? Yeah, sure, Mary. Let's do that. Long off start stay. We got this. And then we'll go back and we'll do that here in 2 seconds here. So here's what it's going to look like, Charlie. It's going to look like B1 plus or minus T star. And what happens with a very small sample size? If your sample size is very small right here, Charlie, what's going to happen to your margin of error? With a very small sample size, if you notice, you can't even use a too small of a sample size. You can't use a sample size of like 1 or 2. You have to have a sample size of like 3 or 4 because you can't get it if you only have a sample size of 2. So you have to have a sample size greater than 2 for this equation to even work mathematically. But what do you notice about if for smaller n's, what will the margin of error be for your confidence interval? So your confidence level is dictated by what's shaded in the green. That dictates your confidence level, but then margin of error is larger for smaller samples because you'd have more uncertainty. And if you have more uncertainty, what happens to your interval? Your interval gets wider. And if your interval gets wider, you're more likely to fail to reject the null. Is this connecting? Does this make sense? This is what I wanted to point out right here. Because if you have more uncertainty, you'll be more likely to fail to reject the null, which means you're more likely to make a type 2 error rate, which means you have a less powerful test. So this is what people do, and this is if you notice what this confidence interval looks like, this looks just like all the other confidence intervals we built. We just built one a few days ago, y bar plus or minus t, and we had s over square root of n. Isn't that such an easy thing to remember, rather than the sum of the residuals right there, because that's the residuals for the model, the actual minus the predicted squared, the sum of the squared residuals, so it's the sum of the squared error. And then we have right here the sum of the squared distances away from the mean of the x, and we divide those to do the ratio, and we square root it to take out the squared units, and then we times it by this right here, which is relative to the sample size. Ugh. 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 Don't like that equation. Don't like that equation, but if you look, you have the same components up there, and it's literally the exact same components as we always is. The last thing we do, then we do the other question right here. It's the same components as this is the estimate plus or minus, and this is your confidence level, and this is your standard error. So like p hat plus or minus z. Oh my gosh. There we go. Okay, let's do this. The last question is, could we go over the recent poll one on the quiz? Yeah, let's do the recent poll one. Okay, a recent poll. What is the recent poll question? I need to turn off the heat. A recent poll. Chapter 16, quiz, replace question. Okay. A researcher develops. Poll. What is the start of the question? A recent poll? Oh, here we go. Here we go. We found it. Okay. A recent poll of 1,100 randomly selected adults of a presidential approval rating stood at 48%, making 95% confidence interval for his approval rating by all adults in the country, based on the confidence interval test the null hypothesis of 48%. And so we have to use our equation right here. So we are going to do a confidence interval. We could code that. Oh yeah, we could totally code this. And actually, this is really easy in code right here because we've got the numbers. Let's go over here and hop and do it into Word real quick. So what is 48%? 48% is going to be p hat. And that makes q hat equal to 0.52. Oh, yeah, that'd be so much easier. In truth, we don't even need to code it. Everything we found, or everything we were running right there, Charlie, is given to us right here. So these standard errors, we don't even need to code it. It just, whenever you do a summary of a model, it just gives you the standard errors. So these standard error values are the ones that we would have to solve by hand. We don't solve that by hand. And n right here is equal to this. So yeah, that's why you don't usually have to worry about solving things by hands in statistics. It's just, it gives you the number. You just have to know what the number is. That's why I don't have that number or that equation memorized. I'm trying to stick it in my head, trying to remember it. And I think this said 95. I'll write the equation after this, 1 second. I think we just wrote this out. I just wrote this out a second ago from the other sheet. I'll make it look prettier. P hat plus or minus Z star P hat. Yeah, no, I try to do that. I try to understand why the equation is that way too. Understanding the components. Try to do it. I really wish I want to understand why everything is everything and the theory of everything. Try to understand it all. So we're going to solve this equation right here. So 0.52 times 0.48 divided by this times 1.96. Was it 95? Oh yeah. So that's going to be from this applet right here. So a 95% confidence interval. Let me double check to make sure it wants 95% confidence. So it'll be this number right here, a z-score for a 95% confidence interval, and it is 95% confidence. So does that make sense right there, Mary? It's the z-score for a 95% confidence interval. So that's where the 1.96 comes from. It's the z-score. Does that hopefully make sense right there? Lost my spot on this. So it is the z-score for a 95% confidence interval. And there we go right there. And that's got it. It's basically 3%. It almost rounds to 3%. Almost got it. And so is it to 3 decimals? Such a bummer. So we're just going to go plus or minus here. We're going to take 0.48 minus. Thought it was a lot longer ago. Yeah, I know. It's kind of a review. It's like a review question. 0.45. Is it really? And then... So that rounds to 51, right? Is it going to do that? So do we think, based on this confidence interval test hypothesis, that 48... Wait. They picked the number that was at the center of this interval, so we fail to reject it. It's at the very center. They picked the number in their random usage of numbers that's at the very center of this interval, so you can't reject the number at the center of the interval. That's what we observe. It's like, we saw in a poll 48% of people approve of the president. Do you think 48% is possible? And you're like, yeah, that's what we saw. I think that's a very possible value. I don't reject it. Anything outside the interval we would reject. Anything inside the interval we will not reject. That's got it. Good deal. We're going to head off here. I'm going to be teaching here soon. I'll see everybody later. Great questions. Mary, thank you for coming by asking that question. I'm sure a lot of people are going to be working on it. And so we're going to head off right here. I'll see everyone later. Bye for now. Bye.